and he will give us an overview about QtQuick under the hood. So welcome, Thomas, on stage.
Okay, thank you, Bernard, and welcome everyone to my presentation titled QtQuick under the hood. I hope you've been enjoying the conference so far. We had many interesting talks, both about QML and both about QtQuick. And I have to admit, the title of my talk is actually a lie. It is not actually about QtQuick, it's about the QML engine. So a bit about myself. I'm Thomas McGuire. As Bernard mentioned, I work at KDAP. The guys organizing, or most of the organizing of the conference, and the Qt consultants. My first contact to Qt was through the KDE project. So KDE is the Linux desktop built on top of Qt. And nowadays I work at KDAP mostly. So the motivation for this talk is that I like to know how things work internally. I don't like magic or black boxes. I always need to find out how something actually works. So when I got my new phone, it's an Android phone, so it was possible to flash it. I asked myself, okay, how does it actually boot? You know, there's a bootloader. Okay, who loads the bootloader? And it turned out it was another bootloader. And is it bootloaders all the way down? I didn't know. So I looked it up on the internet, how my phone boots. That's one example. Like, I'm just curious of how that worked. Huh? You can talk to me afterwards. It's pretty interesting, actually. Especially what the first steps of the boot process are. Or for example, the new Lambda feature of C++11, one of my favorite features. How does it actually work? What does the compiler do? So I just had to look it up and read about it. And this is not just to satisfy curiosity, right? Everyone wants to know what it does, but it's actually useful. For example, if you know how CPU caches work, then it's actually useful for the C++ programs because you know about the fault sharing problem in multi-threaded programming. So even though these low-level details mostly don't come into contact with them, sometimes they're quite useful to know about. And this is what I also did with QtQuick. So I've been using QtQuick for some projects. It's very nicely documented, so using it is actually quite easy, but I was always in the back of my head asking myself, how does it actually work? So someday I decided to find out. So the documentation for using QtQuick is quite detailed. Very good, actually, but the documentation on how QtQuick internally, what it does, is non-existent. So what I had to do is look at the source code. So I read the source code, I experimented a bit with it, and today I want to share my findings and explain to you the magic behind QtQuick and what the QML engine does. And this talk will roughly have two sections. Firstly, explaining how the QML engine works. Then the second part is explaining what sort of clever optimizations the QML engine does and what sort of optimizations you can use. So let's start with the first part and examine how a QML file is loaded. So you know you have a .qml file on your disk. Through some magic, it gets loaded, and after that you see a window with pixels and with stuff on it. How does that magic happen? How does it go from the QML file on the disk to pixels on the screen? That process I'll examine now. Of course, we start with the usual example, a hello world example. Let me just run that. So I've got Qt Creator here. I guess who has used QtQuick before in here? Okay, so this hello world example should be familiar to every one of you. It's using a light steel blue rectangle that is demo tradition. If you demo about QtQuick, you have to have the color light steel blue in it. Apart from that, it's just a standard rectangle with a text in it. And if you look at this, it's quite easy to understand, isn't it? There's a rectangle somewhere, there's a text element somewhere. The text element is somehow centered inside the rectangle, and the text element has a text that says hello dev days. Quite easy to understand, but I don't know QML. Where's my C++? I am familiar with C++. How does that relate to C++? The answer to that is all the QML elements you see here are actually C++ classes. So the rectangle element here, that's a C++ class. So someone wrote a C++ class. Because of that, the QML engine can instantiate that class. Same with the text element here. And if you look into the Qt source code, there's actually no class called rectangle. There's a class called QQuick rectangle, and there's a class called QQuick text. So what QtQuick does, it has a registry of known QML classes. And at startup, QtQuick calls a function called QML register type, where it tells the QML engine, okay, there's a class named QQuick rectangle. Please make that available as rectangle in QML. Same for the text element. So there's a central registry of classes. And these classes all have to be derived from QObject. So the QML engine, when it loads the file, it has a parser. Then it parses the file, it goes through the file, and when it notices, oh, rectangle opening braces, that's an instantiation of an element. What it does is it simply instantiates the C++ class. So here it would simply new or allocate a QQuick rectangle. That's the first step in QML. Simply instantiating all elements that have been registered with QML register type. QML register type happens automatically by QtQuick for the built-in types. Then there are these properties, right? We have color here, we have text, we have this anchor stuff. These are called properties. These properties correspond to properties in C++ as well, QObject properties. If you look at a header, so I got the source code here for the QtQuick rectangle. You can find that in the Qt sources. So as I told you, class QtQuick rectangle, and it has a bunch of properties here declared with the Q_property macro. Because of that, the meta object compiler creates special glue code for introspection. So at runtime, you can ask QMetaObject, please list me all properties of the QtQuick rectangle class. If you want to know more about that magic, introspection magic, yesterday was a great talk from Stephen Kelly explaining how that works. So I won't go into the details now. It's sufficient to know if you declare a property with Q_property, it's known at runtime, you can do introspection with it. So you see here we have our color property declared. And that's what the QML engine does when it loads a file. When it sees color here, it does introspection and asks QMetaObject, okay, what's the property? Color, does it exist in rectangle? And if it exists, it uses the setProperty method in QObject to assign the property value light steel blue to that color. And same with text here. So basically all that the QML engine does is it instantiates objects and it assigns properties. That's done when the QML file is loaded. After that, the QML engine is done and it disappears. After that, it's all C++ code and the QML engine is not involved any longer. And as I said, these types, elements have to be, they are in the central registry. The properties are known because of the meta object system Qt has. You also have signals and slots available in QML. We'll come to that later. It's also done by the meta object system. So that's quite easy, right? No, not much magic actually in the QML engine. Yes? Yes. So he was asking, are all objects instantiated on the heap? Yes, they are. So, yeah.
Can I instantiate these objects on my own
No. Well, you can, but the thing is, the classes like QtQuick Rectangle are private API, so they are not made public. You can use QMetaObject magic maybe to get a hack and get QMetaObject system to instantiate them, but in general, no. QtQuick, they made a design decision to not let you instantiate these classes in C++. Okay, so let's see what happens in our Hello World example step by step, right? If it says import QtQuick 2.0, it actually loads a plugin. In QtQuick 2, that's libqtquick2 plugin.so under Linux. This plugin, when it's loaded, it has a startup hook that calls all the QML register type functions and registers all classes like rectangle, text, and all the others. So after that import statement, QML knows about the available types. And it sees a rectangle, it will simply allocate a QtQuick rectangle. So that's a little lie. It will actually call QMetaObject construct. Reason for that is, of course, it doesn't know about QtQuick rectangle since it's a plugin, so it can't instantiate the object directly, so it needs to use the factory method of the MetaObject system. But that's basically the same as this one. And because QML engine doesn't directly know about the type, we have to do everything to the QObject pointer. So instead of saying rect.setColor, we have to say setProperty, because we just have the QObject pointer. So that's what the QML engine does. Simply calls setProperty on the color property. Then it instantiates the text element, takes care of parent-child relationship here. So the text element will be a child of rectangle. Then it sets the anchors. That's actually a nested property. So the anchors property, if you look in the source code, that's a property of type QObject. So it first gets that and then sets the sub-property, so to say. Then, of course, setting the text is the same as setting the color. And that's it. Quite easy, right? If the headers weren't private, you could do that in C++ as well. In a sense, it's quite similar to UI files in widgets. UI files in widgets also create similar code, right? They create code that creates a push button, puts the push button in a layout. But widgets code, designer UI files, they do that at compile time. So when you compile your UI file for traditional widget projects, it will create similar code like this, but at compile time. And the QML engine does that at runtime, and with a much nicer syntax than the XML files in widgets. It's so similar, actually, it was called, the QML project was called UI2 inside of Nokia for a long time. So far, we've seen that all the QML engine does is it instantiates objects. And that is, it is. And that also means QML doesn't know anything about the UI. So the QML engine is completely UI agnostic. Someone else needs to take care of the UI. And in QtQuick, so there's a differentiation, right? libQtQML, that's the engine. Then you have libQtQuick, that are the UI elements. They're two separate libraries. And libQtQuick has all the items and it takes care of rendering. All the rendering stuff is done by QtQuick So what QtQuick does, it uses the engine to load a QML file. The engine will return the pointer to the root object. So then QtQuick has the root object. And because of that, all the object tree of the objects the QML engine instantiated. Once it has that, it simply iterates through the complete object tree and renders each element. If you look in the header of QtQuick rectangle, for example, you will find a function called update paint node. That's what QtQuick uses to render the items. It's a bit more complicated than that, since there's actually a scene graph engine that does OpenGL rendering in a separate thread. But in principle, That's all done by this QtQuick view class. And because QML engine is UI agnostic, it means you can actually put up other stuff than just QtQuick. Right? It's not limited to QtQuick. You can come up with your own items. You don't need to use QtQuick view. You can use something different. That's, for example, done in the BlackBerry 10 OS, which uses a library called Cascades for the new upcoming BlackBerry phones. And Cascades is built on top of QML, but they ship their own items and they ship their own renderer. So Cascades has something similar like QtQuick view, maybe something called Cascades view. So Cascades is a completely different renderer and completely different items. Same with QBS. Who has heard of QBS before? Yeah. So for those who don't know, that's the build system built on top of QML. So we can, instead of having the .pro files or CMake files, you write your build system in the QML language. So that's a research project going on inside Digia at the moment. Quite cool, right? It doesn't even need UI. QBS doesn't have an UI. It's a build system. But it can utilize the QML language. And then I'll now show you a world premiere, something my colleague wrote. So this application here is a standard text editor. Nothing difficult about this, right? Standard widget-based text editor. You can use file dialogues and all the other widget stuff in it. Guess how that was written? Yeah, QML. So what we have, okay, which of these are main.qmls is the correct one? Was it? Oh yeah, this one actually. So this widget application was written in QML. I simply instantiated the widgets in QML. Complete text editor written in QML. That's quite cool, right? So, so you have to applaud my colleagues. Two of my colleagues came up with that. Basically, I wrote little wrapper objects for all the widgets. Because the widgets are like they're missing some properties and so on, so they added little wrapper objects. Then you can simply instantiate them. Quite easier. Instead of extending the Qt component set, which is a lot of work, this was actually quite easy to do comparably. And you have all the standard widget stuff. So it's also possible to do widgets. So it's not released to the public yet. I think at some point my colleagues will make an announcement and publish that. And by the way, if any of you guys knows a good tool to create diagrams under Linux and have some recommendations, since this is not very nice, please talk to me afterwards. Okay, so that was the QML engine. It parses the QML file, creates objects, and assigns properties. And then it's done. Everything else, like rendering, is then done by someone else, like QtQuick view. Now I'll talk a bit about how the two different worlds, QML and C++, interact. So far we've seen the QML engine instantiates an object. But what you can also do, you can instantiate an object in C++ and tell QML about that object. That's actually missing a call to root context here, so it can fit on the slide. Basically, you call set context property on your object pointer, and it will be available to QML under that name underscore CPP object. We use underscore as sort of notation to easily see in QML, okay, that thing has an underscore that's instantiated from C++, just to make it easier to read. So that's one idiom we use. And in QML, you can simply use that. For example, in a property assignment, it will then read the property from the C++ object and assign it to the QML object. You can also do, we'll get to the details of this one later, you can also call functions, slots, since slots are known to the meta object system. So you can call functions, and you can connect to signals, all through the meta object magic. And it should come to no surprise to you that you can also do that the other way around. The QML engine creates an object for you, and you can access it from C++. Just logical, right? What the QML engine will do, it will return you the root object of the QML file it loaded. So that's available all the time. If you want to access a sub-element of that, call find child on the object name. Because if you have the root object, you have the complete object tree, and you can basically access every object that was instantiated in QML. Yeah? ID and object name are different things. So object name corresponds to the object name of QObject, and ID is a special QML identifier that is not available in C++. Yes, right. That name has to be unique for this code to work. Once you have done that, again, you can use the meta object system to access properties of the object instantiated from QML. And you can even call functions. So if you have a JavaScript function here, you can use the meta object system to invoke that function. Thing is, do not do this. So if you do this, in your C++ layer, you reach into the UI layer and change stuff in the UI layer, or you depend on your UI layer. That's a violation of abstraction, right? The QML layer should have access to the C++ layer, but not the different way around. For example, if you do it this way, you can't easily change the QML file anymore. You can't give your QML file to a designer, he makes some changes and give it back to you, because he might change object names or rearrange things, then your C++ code won't work anymore. Or if you have one QML file for landscape orientation, one QML file for portrait rotation, which works for the same C++ code, then this one might also break. So that's a bad practice. It was just to show you that it is possible to do this. And you might have noticed one thing that's a bit unusual about this. We know width is a property. It's declared in a header file with Q_property, right? But what about area here? If you look in the QtQuick rectangle header or the QtQuick item header, you won't find Q_property for area. That is, of course, because we added that here. But the meta object system in Qt, that parses the header to come up with a list of properties. So how does it work that I can still access the area property here? Yeah, right, it's dynamic properties. And same with the function, right? There is no slot in the C++ class called say hello. Qt meta object system doesn't know about it, but still you can actually invoke it. And if you look this up in the tool Gamma Ray, that's a free software introspection tool for Qt that we wrote. You can list all your objects at runtime. You will see it says test here, but it should say area. You will see that the property is still available, even though it was never declared in any header. And for some reason, the element name is not QtQuick rectangle, but QtQuick rectangle _QML _0. That's certainly also not in any header, right? And the way that works, it's called virtual meta objects. So at runtime, when the QML engine loads the file, it will create a new meta object itself that contains the area property and contains the say hello slot. It's a similar technique as used in dbus. If you've ever used dbus before, the QtDBus bindings, you can also have slots for all the methods in dbus, even though that they aren't available in a header. So dbus uses the same technique. Actually, a class in Qt core called virtual meta object builder, which you can use for creating your own meta objects. So the virtual meta object technique makes this area property and the say hello function available to the meta object system. Okay, when I told you all the QML engine does is loading a file, creating classes, assigning properties, I lied to you again. It does more. It doesn't disappear after file loading because it can do JavaScript stuff. If you look at this example, there are 3 different cases where there's JavaScript code. We've got a so-called binding here. This is a complex expression that is evaluated by JavaScript. There is a bound signal handler, that's what it's called. It's basically a signal, it's like a slot basically, that has JavaScript code that is evaluated. And then you can have freestanding functions like I will say hello, also evaluated by the JavaScript engine. So what the QML engine actually does when it loads a file, when it sees a more complex expression like this one, it will invoke a JavaScript engine, V8 in this case, to evaluate the expression. Then it gets the result, and it calls that property with that result. Or this bound signal handler, there actually the QML engine will create a little helper object with a slot, connects that to the clicked signal of the mouse area, and in the slot it will evaluate the JavaScript. So the JavaScript engine used for that is called V8. It's part of, I think Google invented it for their Google Chrome browser. It's supposedly faster than JavaScript Core, which was used in Qt 4. So now the question is, of course, we have got a height and a width property here. How does the V8 JavaScript engine know about that? It's not built into JavaScript, right? Or actually, how does it know about the parent object? And the way that works is, the JavaScript engine evaluates that expression. As soon as it finds a name of an object or of a property that it doesn't know about, it will call help. I don't know what I have to do. I don't know this parent thing. And it will ask the QML engine in a so-called wrapper. So it will reach out into the QML engine. Okay, dear QML engine, tell me what this parent thing is. And the QML engine will do that, look it up in its context scope, and return it. Same for a property. V8 will cry for help. Okay, I've got this parent object, that's nice, but does it have a height object? And if yes, what's the value? QML engine, please help me. So it will call this QML wrapper function. That then does the property lookup in the meta object system and returns the value. That's all you need to know about how JavaScript works. Not difficult, the clue code is in the wrappers. So JavaScript can access objects and properties. Let me show you some example again. So this is our example I've showed on the other slide. There's a complex property called area, and the JavaScript engine evaluates that when it loads the QML file. But there's more. If I resize this, the area changes by magic. It's automatically somehow the value for area is recalculated. How does it do that? So it's not just when loading the QML file, somehow it must update this binding later when either height or width changes, right? How does it do that? And the way that's done is there's so-called change signal in C++ classes, which you declare with a so-called notify keyword. If you look in QtQuick rectangle again, oops, wrong class. QtQuick rectangle. There it is. You will see that, for example, the color property has a color changed signal, a color changed notify signal. And the C++ code is responsible for always emitting that signal whenever the property changes. And the QML engine connects to that changed signal. It creates a little object again with a helper slot, and whenever the signal is emitted, the slot is invoked, and the slot will re-evaluate the JavaScript binding again. Right? Not much magic. So we have two connections here. We connect to height changed and width changed, and to one slot. In that slot, the JavaScript expression is re-evaluated. Also not much magic. Just that's all done automatically, so you don't have to come up with lots of connect statements in your code. The interesting thing, of course, is how does it know what changed signals to connect to? In this case, it's easy, right? We know it's height changed and width changed. But the object, like parent, might not be known at loading time because it might be an object coming from C++. So this is actually dynamic. When the QML engine loads the file, it doesn't yet know what the parent object might be. So it can't yet connect to the changed signals. The magic, how it solves that, again, lies in these wrappers. And when the JavaScript expression is evaluated for the first time, and JavaScript wants to know what this height thing is, it calls into the wrapper to ask QML about that, right? And what QML does, it has a list of properties that were accessed, and it just puts height into that list. Later, when JavaScript asks for width, it also puts that into the list. This list is called the captcha list. So QML has a list of captured properties, and once the JavaScript expression is evaluated, it goes through the list and connects to each of the signals of the properties changed signal. That's called property capture. And it's even quite clever. If you have an if statement in your binding, it will not connect to the property changed signals that are in the branch that was not taken, because JavaScript never asked the wrapper for that property. So it will really only connect to those it needs to connect to. So these property things are called bindings, and in my opinion, that's the magic that makes QML really a declarative language. Since you can simply write an expression like this, you declare what text is, which is very declarative way. You don't have to write imperative statements like a connect statement, another connect statement, a slot, which you have to declare in the header and you have to add it to your CPP file. That's at least 7 lines of code, imperative, boring code, and QML does all the magic in the background with 1 line. Quite cool. So now that you know how bindings work, right, it's just JavaScript code that is re-evaluated whenever such a changed signal is emitted. Of course, we know what to pay attention for. If you forget to emit the changed signal, so if you change a property value without emitting the changed signal, the QML engine will not know that it changed, and it will not update the binding. That can lead to subtle bugs, right? Who had this happen? Did it happen to you at some point? Hands up. It happened to me, right? Happened to the best of us. You look at your UI, it doesn't update. Oh, what's happening? That's, of course, you forgot the changed signal. So the best practice for that is don't change a value directly. Always call the setter, and in the setter, emit the changed signal. That reduces the possibility of that error quite a lot. The other thing, of course, is the opposite. You can emit too many changed signals. Like, if you emit width changed, even though the width didn't change, the JavaScript engine will kick in and re-evaluate the expression, even though that was completely not needed. So you should avoid that. And again, there's a general pattern, an idiom in Qt. If you look at the implementation of QtQuick rectangle, you'll see if the value didn't actually change, it will return and not emit the changed signal. So you should always do the same as well in your setups. That avoids some of the unneeded updates. Then, if you have items that are not actually shown, and they depend on a property and the change signal for that property is emitted. Even though the item is not visible, the binding will be evaluated. Because again, the QML engine doesn't know about the UI. It doesn't know whether an item is visible or not. We had that problem in one project where we had a volume meter updated every 50 milliseconds when the volume changed. And even though the item wasn't actually visible, it wasn't on other screen, binding was always updated, which caused slowdowns when scrolling through a list, for example. And the way we solved it, we checked in the code that emits the signal, we checked if the item was visible, and if it wasn't visible, we didn't emit the signal. We made our C++ code depending on the UI, which you shouldn't do, but it solved that problem. Then you have the Kraken. I call it that a Kraken is a changed signal that reaches out with its many arms and changes, updates lots of bindings all over in your QML code. Right? If you use a property in many bindings, you will get many updates of bindings. So that's something we also had in the project. So you have to watch out for that as well. Let's actually skip that. Okay, so QML engine, it creates objects, assigns properties, right? That's almost all it does. It does have some virtual meter objects for the additional properties. It has bound signal handlers. And it has bindings that are evaluated with JavaScript and updated whenever you get a changed signal. So let's have a look at the clever tricks the QML engine uses to make things faster. First of all, a thing for you, if you have a QML program, always use the QML profiler to see out, to look what might be slowing down your application. So the QML profiler is built into Qt Creator. It can detect whether there are too many binding updates, like the Kraken. It can detect if your QML file loading is too slow, if you load too many QML files at once, or if the painting actually takes too long. And QML in Qt4 might be because there are lots of text elements and text rendering is slow. So what I told you earlier, how QML file loading works, of course, was a lie. So there is actually no QML parser which goes to the QML file, then does all the stuff I described. That would be way too slow, right? If you have a button.qml and use that button dozens of times in your project, having a parser each time that button.qml is instantiated would be very slow and a waste. Of course, the QML guys noticed that and came up with a clever optimization, which is called the virtual machine environment. So instead of at load time doing all the things manually, it doesn't do them, but puts the instructions in a list. For example, in button.qml, it might put an instruction, create a rectangle instance in a list. Then it might put the instruction, assign color light steel blue to property color. So it creates lots of instructions and saves that in a list of instructions. That's done once. So whenever a button.qml is instantiated, for the first time it creates this list of instructions, and at the second time it simply needs to iterate over that list of instructions and execute those instructions. These two phases are called compiling and creating. You will see them in the QML profiler. So compiling creates the list of instructions, creating executes them. And if you're curious on how that looks, there's an environment variable QML compiler dump equals 1 you can use to see the kind of instructions your program uses. Like for the button. So these are the instructions created for our button.qml. For example, you have create CPP that instantiates a QtQuick rectangle. You have store meta that creates a virtual meter object. You have store color that calls that property on some index, which happens to be the color property, and so on. So the QML engine does that to speed things up a bit. In your QML, you have basically two different ways to load your UI. Now, a UI is mostly composed of multiple screens, which are not all visible at the same time. What you can do is you simply load all the screens at startup in one big QML file and simply set the visible property to false. Or you can use loaders to load screens and items on demand. The first method, of course, your startup time will suffer. And if you use loaders, then of course the dynamic loading of the screens when an action happens might also incur a delay. And in QtQuick2 or QML2 in Qt5, you can now set a property on the loader called asynchronous true, which will load a QML file in the background, in a different thread actually. So the compiler and the VME, which interprets the instructions, are loaded in a thread. So you can combine the best of both worlds. Load all QML files into memory at once, but do it with an asynchronous loader so your startup time won't suffer. That's quite nice. So when I told you about JavaScript bindings, which are evaluated by V8, the JavaScript engine, that was a lie. It doesn't always do that. It actually has a thing for optimization reasons called V4, that's a pun on the name, which doesn't use, well, it compiles the binding into a bytecode and then interprets that bytecode. Right now, the V4 engine only understands simple expressions, so doesn't understand all of them. So for more complicated stuff, QML will fall back to V8. But for simple bindings, V4 will be used. That's bytecode interpreted by the QML engine itself, not by V8. Basically, it works like a CPU does. It has registers, it loads a property into a register, can multiply two registers, then it can store or write back a register to a property value. There's also an environment variable, QML binding stamp equals 1. We can have a look at that stuff. So this is an example of one optimized bindings, one V4 bindings. As I told you, it loads stuff into registers, operates on those registers, and then writes it back to a property. Now, V8 compiles into machine code, right? V4 compiles into bytecode. Isn't machine code faster than the bytecode interpreter? That's what I was asking myself. Like, that doesn't make any sense. I benchmarked this, like a small program that updates a binding 1,000 times. I benchmarked this, and indeed, V4 turned out to be faster. That's probably because V8 has lots of overhead. You know the wrappers, when JavaScript needs to call out into those wrappers to look up properties and objects, that is overhead. JavaScript is quite dynamic language, which also causes overhead. V8 might recompile your binding because for some it thinks that it will be faster afterwards. That is overhead. So altogether, for simple bindings, V8 overhead is simply so much the bytecode interpreter is faster. And if you have seen last keynote yesterday, he talked about iOS and that V8 doesn't work on iOS because iOS doesn't allow dynamically compiled code, jittered code. So the solution for that is, as Lars said, is come up with a custom JavaScript engine. This one is based on V4, so it's roughly the same concepts as V4. And it's currently in development. There's a playground project on Git with that new JavaScript engine. And at some point, this new one will replace both V4 and V8, which we have. Advantage is apps will work on iOS. Since this new engine will have a bytecode interpreter, also called a VME here. And of course, a bytecode interpreter is allowed on iOS. If you're not on iOS, you might want to have something faster, then it can compile into machine code. using either LLVM or some custom machine code generator. I don't know why they have both. I only heard about this project on Friday. But that is the future of JavaScript engines within QML. It's a small, lightweight engine optimized for little things like bindings, and it doesn't need to have all the overhead V8 has. One small thing about fast properties. You know, all the property access is through the meta object system. We've seen that it calls set property or get property for connect statements. When it connects to a binding changed signal, it needs to connect to that, and when the signal is emitted, it goes to the meta object layer. For connections, the QObject keeps track of a connection list, so there's quite a lot of overhead in the meta object system. And of course, the QML devs also noticed that and came up with a way to make this faster, which is bypassing all the meta object system. So instead of going through the meta object system to read properties, the so-called fast properties can read the value directly. You actually give it a pointer, for example, to the int. If you have an integer property, you give it a pointer to the int, and all the meta object system is bypassed completely. Same for connect statements. Instead, you have a QML notifier we simply call notify, and it will bypass QObject and all that overhead completely. That is not yet public API. For one reason, it's still, you need to write a lot of macros, and it's not very nice to use at the moment. I hope they will improve that and actually support fast properties in QObject itself. But right now, it's not there yet. Therefore, it's private API, and I hope that will be available soon. And of course, it's a bit complicated to use. So I've done that in an example project. Let me see. So I cheated and included private headers here. Of course, you can't do that because it will break binary compatibility and source compatibility at a moment's notice. But you can see here, you use a lot of macros. There's a property called counter, which I added to the fast properties. At the moment, you have to use a lot of macros. You give it, you give it a pointer, basically, to your variable of your property. And for the change signal, you even have to write some functions which somehow involves the QML notifier. So, and there you see, instead of calling emit, you call notify on the QML notifier. So right now it's not really ready for prime time use. I hope it will be soon, because it gives you a little bit of performance. This is again an example where I updated, I think, a binding 1,000 times through the changed signal. So my hope is that this will be available at some point. So my last slide, two final things. There's a thing called QML min, which minifies your QML files. It will remove comments, white space. It will simplify JavaScript. My hope was, I run the tool, I see that it's faster, and I add new nice graphs to my slide. Well, I was disappointed it doesn't make a difference in performance at all. It's mainly useful to make your binary size smaller, your executable size, if you compile your QML files into your executable. And do not ever check these files into a version control system, the minified files. If you do so, your next life you will be reborn as a Visual Basic programmer. Then there's a thing called final keyword, which you might also have noticed in, for example, the QtQuick item. All these properties are marked as final. That means it gives the QML engine certain optimization opportunities because it knows a property is not overwritten in a subclass, which can make property lookup in QMeta object faster. So it's a good practice to always add a final keyword to your property unless you intend to override it in a subclass. which is quite unusual. I haven't really found a use case for that yet. So use this one. It's good practice. It doesn't cost you much, and it's easy to do, and it will improve performance. So if you want to know more about how the QML engine works, have a look at my blog. I intend to blog about a bit more, like explaining how value types in QML work. Simply search for QML engine internals. You don't need to remember that URL. Have a look at the Qt documentation. They have quite excellent documentation, especially about the UI stuff, which I haven't talked about, and how you optimize that. And the applications I showed here are available under that URL. For example, if you want to have a look at the fast properties thing. Okay, everyone ready taking pictures? Yeah, finished? So the slides will be online as well, I think. So you can download them later instead of taking pictures now. And that is it. We learned a lot about how the QML engine works. You now know what the magic behind it is. And I hope it will help you in applications. And if not, you satisfied your curiosity, I hope, how it works. And if you're too shy to ask questions now, you can send me an email or use this Twitter thing to send a tweet to me. And if you're not too shy, please ask your questions now. Yeah, and wait for the microphone, I guess.
Okay, thank you, Thomas.
Yeah.
Any questions?
Hi, thank you for the great talk. It was cool. Is it possible to generate QML objects and properties on the fly? So not writing all the properties in a QML file fixed, but in C++ generate it all dynamically.
Okay, as far as I know, QML doesn't have support for dynamic properties. So either have to use the Q_property macro in C++, or you have to use the property keyword in your QML file, but there are no other ways to create properties. Well, you can probably use the meta object builder yourself to add static properties to objects. But as far as I know, the meta object builder is private API in Qt Core right now. Okay. That would be the only possibility for that.
Okay, thank you.
Thank you too. Maybe you're not the exactly right person to ask because you're not the one who wrote QML and QtQuick, but there are many talks and questions about how or if it's possible to secure some kind of the QML text, because people complain about that this text is included in the final application, can be changed very easily. So it's maybe a bad idea, don't know, but if there's already a compiler for it, the V8 or the JavaScript compiler, wouldn't it be possible to use the compiled bytecode as inclusion in the final program?
So that is actually a good idea, not only because your code would be secure, but also because you don't need to compile at startup, right? If you simply save the list of instructions for each QML file on disk, it would be, well, more secure, security to obscurity, but hey, it would be more secure, and it would be faster at startup. I think it would be possible, it's just simply no one has done the work yet. So I've seen talks in the mailing lists from the QML devs, yes, that's possible, just someone needs to implement it. And if you want to use security, just use an encryption key to encrypt your QML files and then load them, decrypt them, and then pass them on to the QML engine.
Thank you. Is it possible to delay the actual binding to the point where it's used by the rendering code? So for instance, if I send signals in 10 millisecond raster and I'm painting 1 second later, I would only need to bind once instead of every 10 milliseconds.
No, that's not possible right now. If you have problems with too many binding updates, you have to change the C++ code to not emit as many change signals. So if you want to have more control over that, you have to change that in your QML code. Actually, what I tried once is to hack the QML engine if the object is not visible, to not do binding updates. Like I had a UI dependency in the QML engine that sort of worked, except that the visible property itself wasn't updated anymore. So the well, but yeah, you have to do it in C++ at the moment.
I have a question about the management of the loaded QML files. You say you can load it asynchronously, and can you also manage how, in which pattern they are unloaded? So if you browse through your QML application with all screen, are you able to manage how many will be cached and or not? Or if they're all loaded, are they loaded and stay loaded?
As far as I know, they are all loaded. I don't know about the order of loading and destruction, but they're all loaded unless you use a loader. So they're all by default loaded into memory, and the compiled stuff, like the instruction list, stays in memory, I think. But I'm not sure. It has some sort of cache internally, but for that I don't know the details.
So it will eat up the memory if you have a large application. Will in the end eat up all the memory, even if you
theoretically, yes. So I have to say we had applications with more than 100 screens on a computer running 256 megabyte of RAM. We didn't have a problem. So if you use a loader, well, we can maybe talk later and find out the details. So it might be that it unloads the data if you use a loader. It will probably actually, and maybe they have a cache and it's full at some point, but we have to take that offline and look at it later. So I don't know the details.
How do the QML engine evaluate the ID?
Okay.
The question is, if you load some library and they use IDs, they are still visible to your program. So if you by accident use an ID, then it's somewhere weird because you don't know if it's by accident referring to the library's ID or if it's your own ID you set somewhere in your program.
The ID in QML is a bit special. It's not a property, it's a special keyword. And the QML engine uses that in a context scope. So it has name lookup rules for IDs, similar like you have name lookup rules in C++. And normally IDs of an object shouldn't leak out into the parent because the name lookup scope prevents that. Similar to like in C++, if you have a variable in a function, you won't have access to that outside of the function. It should be the same for QML elements actually with IDs.
You can reference the ID from outside the item.
Ah, right, yeah. Oh, right. It actually has special name lookup rules for that. But that only happens if you write your ID inline in the QML code. If the ID is in a different QML file, you won't see the ID. So it's local to the QML file and it won't leak out.
You will see the ID. Yeah,
really?
the Qt components makes great use of this technique.
Really? Oh, wow. That's a bit surprising.
Yeah, even if you introduce very global variables there.
Yeah, I'm not that familiar with the lookup rules of the ID. It might indeed be, as you said, and well, that's weird, but well, if it makes components work, why not?
Yesterday I talked with Walter about the thing, and it's considered a bug, actually, but it works, and it shouldn't be used, because there can be time it will be removed.
Yeah.
But actually you can refer an ID when you have a hierarchy of items, and you refer from the lower one to the ID of something from parent.
Yeah, okay, it's good to know that it's a bug because it would break encapsulation of stuff. So I'm happy it's just a bug and might be fixed.
Just to say about this, it's the same with properties. So you can build in a parent, you can make a property, and then in a lower case you can call that property.
Right, okay.
Okay. Okay, thank you. Time's up.
Okay.
Yeah.
Okay,
Thanks
thank
again,
you, everyone.
Thomas.